what we're going to do is we're going to do a couple of activities using matrices to get to answers in a hopefully more efficient way.
So what I'd like you to do, just to start with, is think about some pairs of complex numbers whose product is purely imaginary.
Two teachers who, with their students, help to explore different approaches to teaching further mathematics in the classroom. In this case, the focus is on ways of introducing new topics in further mathematics. Here, matrix multiplication.
We've got two scenarios. The first scenario is you imagine running a pizza company. So this question is about what is the most efficient way of working out how much of each type of topping you need. Second one, Women's World Cup 2015, and it's about calculating the amount of points that each team gets. So again, is there an efficient way, mathematically, we could get the answer?
I think the activities to introduce matrix multiplication were probably a little different than the way I would normally go about doing that. I think with matrices in particular, there's a risk you can end up being quite procedural in the lessons. You know, here's a matrix, here's another matrix, multiply them together. And there's a danger there that you end up getting to the end of the topic and the kids are still sitting there going, yeah, but so why do we have matrices?
The questions are a lot different to, say, in a textbook, because the textbooks explains exactly what you need to do. The questions we were using this morning, you had to read it more and understand what you had to do.
Wouldn't it be 2, 3, 4 that way? So you have
Number of rows in the first
columns, because that equals the number of rows.
Number of rows, I thought number of rows in first equals number of columns.
So are you having a discussion about which way round you're doing the two matrices?
Yeah.
Right, and you've gone for that. What's your thinking at the moment, why you've gone that way round?
Because we can multiply each of these by each of these to work out the total number of toppings for each one to get a 1/4 matrix.
Okay, so you're kind of thinking there's going to be the right number of things there to times those things. Yeah, looks good.
And that should give us a 1/4 matrix with the total quantities of each type of topping.
Okay.
Conversations the students were having, they were definitely saying things like, I know I'm going to have to multiply the number of wins by 3, the number of draws by 1. That would give me confidence that I could give a class that resource and they would be able to get into the problem in the right way and sort of arrive at matrix multiplication. So do you want to share what you've done in your pairs?
So you've obviously got the 4 teams and their results from the 3 matches played.
So the first one would go
so
across.
Do you want to share what you've done in your pairs?
And then the second one would go down like that.
Yeah. So then you can tangent together.
Yeah, so what we've got here would be the answer on the other side.
No, it can't be because it's 4. You can't. Oh wait.
Yeah, because that goes across and there's 3 across, and then that goes down and there's 3 down.
Yeah, that makes sense. Yeah.
Something that's possibly worth saying there is, as teachers perhaps think about the amount of time we spend asking the kids to do things formally versus the amount of time we ask them to spend thinking more creatively, where actually if you make a mistake it doesn't matter.
We had a lot of work on your pieces of paper look a little bit like that. I had some discussion with people about whether this first matrix should go at the beginning or whether it should go at the end.
I think the two activities were very easy to understand scenarios, good little hooks, although the individual calculations that the kids had to do, basically multiplying small numbers and adding them together, they were being done in a matrix form, and you could therefore say, well look, this is a motivation for matrices.
When you're multiplying matrices, you need to make sure that the number of columns in the first one is the same as the number of rows in the second.
So how would you describe the second matrix in terms of its order or its dimensions?
3 by 4, so
it's 3 rows.
3 rows and 4 columns.
Yeah.
Whereas the first one's 1 row and 3.
I think if I was actually doing that activity in a full lesson, I would probably run into it a little bit thinking about, well, I've got all this information about pizzas and pizza orders coming in an ad hoc way. How could I represent that information in the most efficient way possible, first of all? Then I've got a matrix, and then you can start talking about how you manipulate the numbers, and actually matrix multiplication could do that.
And we'll get minus 12 plus 6i is negative 6i.
Here, a slightly different approach, this time with complex numbers.
Some pairs of complex numbers whose sum is a real number. Some pairs of complex numbers whose product is a real number. Okay, so on your whiteboards, just have a quick go, try and find a few pairs for each.
Purely imaginary number.
sort of adding complex numbers, you might do an exercise as a teacher and it can get quite dry sort of quite quickly. What's a great thing to do is that if you provide sort of an immediate challenge and an immediate question that students want to answer, they're sort of more motivated, where they can take the learning in their own direction, but also just some really great tasks that sort of make them make generalisations, actually just having a go at it themselves and trying to spot that pattern rather than sort of being led in their learning to do that.
The value of I has to be the same, but one has to be negative for the other complex number, so they cancel out and it always equals a real number.
Okay, so great. So would it always have to be a complex conjugate, which is what you've used?
No, not necessarily. That could be 3 or any other number.
Any other number?
But as long as the I value is the same but negative in the other complex number, it'll cancel out and always equal a real number.
Great.
2 add 3i minus 2.
Yeah. So again, multiples of each other. Multiples or square the complex number.
You can't have an x value for the last one, can you?
Unless
one of them's...
If one of them is a
makes
0, then that's fine.
So we need to make sure these two times together equals these two times together. It has to be 2 positives, because a negative would make that positive as well. So
Especially ones where you've got all the same coefficient.
Has anyone got an example where the product is purely imaginary, but one number isn't the multiple of the other? Isabel, have you got one?
We had 6 plus 3i multiplied by 2 plus 4i.
6 plus 3i and 2 plus 4i. So there's 2 examples there where it is a multiple as such, and then there's one example where it's a different relationship. Maybe not sure what that relationship is at the minute, but when we expand it, we get a product of 30i.